pleasure to be speaking to this audience for many obvious reasons, but one of which Paula mentioned. You know, I have a training in engineering, so I have a soft spot still there in my heart. But also, this is a paper that's very dear to my heart, and it's part of a big project. And this particular paper has recently been published. I should also mention the names are not here, but this is joint work with Fatih Karahan, who is now at Amazon, Serdar Özkan, who is at University of Toronto, and Jay Song, who is at the US Social Security. Now, I think the title is pretty self-explanatory about what I'm going to talk about today. There's one little twist. So the title says, what do data on millions of US workers reveal about life cycle income risk? And you all are in England. So how much of this, what we are going to talk about today, is transferable across countries? We are right now doing a global project. It's an international project that involves 13 countries with Luigi Pistaferi at Stanford, a colleague, and Gianluca Violante at Princeton, and 51 economists from around the world. And what we are doing is we are looking at the same set of facts I'm going to talk about today. We are looking at these the same facts in 13 countries, including the UK. And the project is actually live. We have a website where you can go and see these facts for yourself, including for England. Okay, so what I'm going to say today will be more broadly applicable than the US, which is the main point I want to make clear. So to frame the talk, the paper, what it's about, think about all the students who are going to graduate or have graduated from UCL this year and joining the labor market, and expand that. Think about all the students who are joining the labor market in London this year or in England this year. In the next 30, 40, 50 years, each one of these individuals, workers, are going to have their own adventure in the labor market, right? They are going to get promotions. They are going to, you know, unfortunately, some of them will get demotions. They will lose their jobs. They will find new jobs. So there will be a 30, 40-year-long story that will be, you know, unfolding in their lives. The question is, these very complicated dynamics happening to a broad set of workers with different skills, different talents, working in different industries. Are there certain regularities that we can summarize about the dynamics of their income over the life cycle? So that is the topic of the talk today, because what the object that we are analyzing is something very complicated, but what kind of regularities that are important, right, that we can say about these income dynamics. So I'm going to frame it in terms of three particular questions. The first one is, what does the distribution of income shocks look like? And we are not the first one to ask this question. As you probably know, the research on income dynamics goes to 1970s. The very first time panel data on income became available, economists started studying these questions in Lillard and Weiss, 1979, Lillard and Willis, 1978, Tom McCurdy, 1981, and so on. So what's new? Why are we asking this question again? Well, one question that I'm going to raise is, are income shocks log normal or approximately log normal? And the reason I'm going to raise that is the overwhelming majority of work out there, going back to the papers that I mentioned, will assume that income shocks are log normal. And I'll circle back to this point and argue that the difference between a log normal distribution and how the data actually looks like is first order. It's not a detail. It's going to be a very important empirical difference. Furthermore, if it's not log normal, is it still symmetrical? Is it skewed? Is there any excess kurtosis and so on? If some of these terms are not super familiar, I'm going to define each one of them, and we are going to just stare at it, and it will become clear what we mean by each one. The second question is an expansion of the first. You know, how do these properties vary over the life cycle as you get older? How do these properties vary across workers in different income groups? And again, we are going to see a lot of variation that's systematic. And the last one is, a question that until recently we honestly haven't even been asking, but it will turn out to be very important. Typically, the way we model these income shocks has been symmetrical. Okay, so we are going to assume that there's an AR1 or an ARMA PQ process. So a shock that's positive and negative will have the same persistence. But is that true in the data? And we are going to see that the answer will be no. They will vary systematically with the sign of the shock and with the size of the shock. Now, I've been saying, these questions, some of them have been out there. What is new? Why are we writing this paper if the questions are not new? Because until very recently, as you very well know, we had very limited amount of data on income dynamics. So the panel data sets that economists had access to in the US, this would be the PSID. You have about 500 to 2,000 households that you track over time. And if you want to get enough detail, this is a very, very small number. UK is not much different. Many European countries had similarly small survey-based data sets, and there are problems with it, with attrition. People stop answering questions, there's recall error, biases, and so on. In this paper, what we do is we draw on the US Social Security Administration data, and this, what you see here is not super accurate. It says as many as 5 million individuals per year. In the last version of the paper, we had the entire US population. So it's a 100%, not sample, universe of all workers. So you can do things, you can relax assumptions, which will be the main contribution of the paper that we have been making for many decades, because we would say, well, we cannot identify unless we make these assumptions. So I have to assume that shocks are log normal. I have to assume that they follow this simple process. So the second, the consequence of moving to a much, much bigger data set is we are going to not follow the traditional way, which is, I'll show you in one slide what that looks like, the covariance matrix estimation. That's the standard way income dynamics models have been estimated in the literature. You can also do maximum likelihood, but in the particular context that this is applied, the two are equal or almost equal. I want to be careful, but for our purposes today, they will be equivalent. Now, there are some exceptions of papers like Megir and Pistaferi in Econometrica and Kostas Megir. I don't know if you know him. He's an UCL, he used to be UCL economist, now at Yale. Martin Browning at Oxford and some co-authors and others. But it's a very small set of papers actually that have gone beyond the covariance matrix estimation. And our paper will be another example. Now, because we have a much larger data set and we can do things without first imposing assumptions on the data, we are going to reverse the order. And that's what I will get in just a second. We'll reverse the order of the research design. We are not first going to write a stochastic process and then go to the data and estimate. We are first going to go to the data without any stochastic process in mind. And we are going to think like an economist and say, what are the features that matter in our economic models? And let me see how they look in the data. Again, if this sounds a bit abstract, hopefully in a moment it will be clearer. But the key idea is we are going to estimate an income dynamics model, not to match some arbitrary covariance matrix for God knows why, but to match moments that we can argue are economically important because we are going to build on decades of theoretical economic research saying that these features are important in our models. Okay, so how do we do that? Let me show you first the covariance matrix approach. Okay, this is a very, you will have hundreds of papers where you will see the structure. Y is the log of income of individual I in period T. And one way we often write this is, it's the sum of a fixed effect. Let me see if I can get. Okay, can you see the red dot on the screen? Okay. So we'll write log income as a fixed effect that is individual specific, doesn't vary over time, plus ZT, which is a potentially persistent AR1 process, plus epsilon, that's an IID shock. And like I said, this is a very, very common specification. The usual approach works by taking this and then deriving formulas for the covariances of this process. And it will look like this. Okay, the variance will depend on the variance of the fixed effect plus the variance of Z and so on. I won't go into all the details and every step. But what you do is you then go to the data and you construct the empirical counterpart. In the data, you calculate the variance of income in year 1, variance of income cross-sectionally in year 2, all the way to year T, and then all the covariances. And then you go to these equations and you pick the parameters like the variance of alpha, variance of epsilon, and so on. These 4 parameters, you choose them such that the model covariance matrix mimics or becomes as close as possible to the data one. In other words, this is what we call the minimum method of simulated moments, or if you want, indirect inference, and so on. Okay, so there are many shortcomings of this approach, but a few that I want to highlight is why the variance. You know, right now, if you match this variance covariance matrix, how skewed income shocks are plays no role in this. Okay, you can match these and get estimates, write a process like this and simulate it. If you simulate with Gaussian shocks, the skewness will be 0. But in the data, it may not be. The kurtosis will be 3, which is a Gaussian. In the data, it may not be. So the higher order moments don't have any say in this estimation because we are not really trying to match them. We only try to match the variances. Again, if you are wondering, is that a big deal? I'll show you quantitatively that actually you can get like an order of magnitude difference in the implications that we study, for example, for portfolio choice, for taxation, for the effects of, you know, consumption savings, pensions. Okay, all of these things can be fundamentally different with higher order moments. Okay, so what do we do here? I'm going to document 4 sets of new empirical facts. When you say new empirical facts, that's always a bold statement. We have not been hit by lightning so far, so hopefully it's okay to say that. Then I'm going to take these and I'm going to estimate a life cycle income dynamics model to match these new facts that I document. And the variance covariance matrix I showed you will actually be one of those, but there will be a lot more important facts that I will match. And the goal is really to provide a user's guide to economists. I imagine, you know, including, you know, people in this audience, when we write models to study certain economic phenomena, right? You know, income shocks, income risk is the primary risk faced by about 99.5% of the population. Their major source of income is labor income. Okay, capital income is really important only in the top 0.1% of the population. So this is the risk that they face in the labor market. So let me start with the data very briefly in the interest of time. The data covers 36 years, 1970 to 2013. It is salary and wage earnings from W-2 forms, if you are familiar with it in the US. This is the official tax document that you get. So, and there is very little wiggle room, so it's very accurate in terms of what your income is. We have also done this with self-employment income, if you are curious, and the results look like anything I will say applies to that as well. We are going to pick individuals aged 25 to 60. What I'm going to show you today will be on men, but the project I mentioned at the beginning, we have men and women together, okay, separately, basically. You can see the differences. They look very similar with some few exceptions. The key advantages, like I said, very large sample size. So you don't need to make the excuse we have about making parametric assumptions doesn't apply anymore. There's no survey, so no survey response error. There's no attrition. You can make 0 income for 20 years of your life. Okay, it's based on your social security number, so you are not going anywhere. It's not like a survey, and there's no top coding. So there will be incomes in the hundreds of millions of dollars, labor income. but there is no information on hours or hourly wages. So everything I will say will be about annual income. So the 4 facts are going to be about, roughly, you can think about the first, second, third, fourth moments of the data. Okay, I'm going to look at the average income growth over the life cycle. I'm going to look at the cross-sectional moments of earnings growth. What I'm trying to do basically, a stochastic process, right, can be an incredibly complex object, right? So I'm going to chop it down into parts that we know how to evaluate, like how much income grows over the life cycle. That's a question that we have some sense about, right? Economically, we understand it's important. If I tell you income goes up by 50-fold, you won't believe me, right? They are not like some covariance that we don't have a feeling about necessarily. Then we are going to look at the cross-sectional moments. And now I'm going to look at the short and long run dynamics. By that, I mean, when a worker receives a certain income shock of a certain size and certain sign, what does the recovery path look like? How persistent is it? Then I'm going to look at, in the paper, at the distribution of lifetime income. We have a completely separate paper on that that's actually forthcoming in October, called Lifetime Incomes in the United States Over 6 Decades. And today I'm going to skip it, but it is actually in this paper, we have a summary of some of those findings, and we are going to match those as well in the estimation. So fact number 1, if you have written any life cycle model, this should look familiar, right? You know, when we write a life cycle model, we feed a hump-shaped income process. This looks like a very smooth function. It looks actually like an exact 4th order polynomial. If you fit a 4th order polynomial, you will get an R square of 0.999. But these are age dummies actually, okay? But they fit almost exactly a quartic. And the rise, I would like you to keep this number in mind. We'll get back to it in just a second. It's about 80 log %. If you exponentiate that, that's about a 127% rise over the life cycle from age 25 to 55. So when we write a life cycle model, we assume that every worker has this average profile, but around this, you know, there's some stochastic fluctuations, but the systematic part is the same for everyone. Now I'm going to go to the data and look more carefully. Here I repeated what has been done before. But now I'm going to go to the data and cut it in a different way. And let me show you, this is a construct I will use again. So let me explain how it works. I observe each worker for 36 years. I'm going to calculate their lifetime income for one cohort from age 25 to 60 for 36 years. And then I'm going to look at the lifetime income over those 36 years. Then I'm going to rank all the individuals, millions of people, by their lifetime income and put in percentiles on the x-axis. Then on the y-axis, I am going to look at the top 1% by lifetime income, and I'm going to ask how much has the income of the top 1% lifetime income earners grew over the life cycle. Okay, did they become very rich because they start very high, they stay very high? Or did they start maybe low, but their income grew very fast? I'm trying to decompose into these two components, so to speak. And this is how the graph looks like. Okay, so let me explain what this is. If you look at the median worker by lifetime income, their income over the life cycle grows by about only 40 log %. So exponentiate that, that's about 50%. But remember, this thing that I showed you, we think it applies to everyone in the population, whereas for the median, those in the 70th, 80th percentile, their income actually grows quite a bit less than that. But you go to the top 1%, this is not like luck necessarily, right? I mean, there's some luck element, we'll come to that, but this is the average of roughly like 250,000 individuals. And their income grows by about 15-fold, not 127%. Now, those of you maybe are thinking there, well, there's something weird here because there's an induced mechanical correlation, right? Because I am ranking people by a lifetime income. Then I am looking at the growth in lifetime in income over the life cycle. if your income grows fast over the life cycle, you are going to end up on the right side. So that is right. If I actually generated income from a random walk, you would get a graph that slopes upward like this. But we are going to, the estimation will account for that. The punchline is this: if you don't allow for systematically different income growth rates, keyword is systematic. Those, and there are theories in economics about this. I mean, the most celebrated theory of wages is the human capital model that won several Nobel Prizes in the last 70 years. The Ben-Porath model, for example, will say workers with high abilities, they will invest more early on, their wages will be low early on, but they will grow very fast over the life cycle. And that is really what you are seeing here, that those whose lifetime income is very high get there by not starting at a very high income, but by growing extremely fast. Okay, if I take a random walk kind of model, the slope would be upward, but would be very flat. It would be like this. I cannot match anything near this curvature that you see here. And it will turn out that that's a very difficult feature to match for any version of the standard income process that has been estimated before. So we need some new feature to account for it. Now that's fact number one. So just to summarize, in the cross section, there are systematically different income growth rates. In particular, those with high income over the life cycle, they get that high lifetime income by growing very fast, not by starting very fast. In fact, those who end up in the top 1%, top 2%, top 3%, about 2/3 of them, of these eventually very rich people, they are not in the top 10, top 20% before age 30. And you might think, yes, they are in school. It turns out, even when they're not in school, because they take jobs that allow them to do human capital accumulation rather than paying very high wages early on. London, the financial center, might be an exception, okay, but this is true for, like, you know, most of the rest of the world. Okay, cross-sectional moments now. I will go with the standard deviation, and I will ask, how does it vary by age, the standard deviation of income change, and how does it vary by income level? Now the construct will be similar, but I'm going to do something more kosher, so to speak, okay? I am not going to condition on lifetime income. I am going to rank people based on their immediately past income. So I'm going to calculate 5-year average income now between T-5 and T-1. Then I'm going to look at the standard deviation of income change between T and T+5, okay? This one is T+1, but the graph looks identical. They are both in the paper. So again, the x-axis now is the measure I just mentioned, percentiles of the recent earnings distribution. The idea is this is a measure of your kind of long-run socioeconomic status, okay? A worker who is on average a high earner, when I look at tomorrow, a year from now, 2 years from now, how much variance in their income do I see? And you see two patterns here. The first one is the higher is the level of your income. Now there is no mechanical connection whatsoever. Okay, there's no endogeneity, there's no possibility of some funny mechanical thing interfering because the time periods are separated. Okay, and these are different moments. I'm ranking by the mean, I'm looking at the variance. So the higher is your income, the lower is the volatility of your income going forward. And the gap is huge. At the bottom 10%, it's 80%. In the 90th percentile, it's about 45%. But notice the reversal. At the very top again, incomes are quite volatile. This is only for young workers. How does it look as you get older? So this will be like a mini movie, okay? This is now when you get to age 30, 34, you get older. As you get older, the whole graph shifts down. So income becomes less volatile, except at the very top, okay? And then you get to age 40, 50, and it stops falling. So then the two conclusions. One, the volatility of income shocks are U-shaped or kind of hockey stick shaped. Okay, they decline for most of the income levels, except at the very top. And two, As you get older, your income shocks become less volatile. Okay, so let's put that fact. We're going to match this one, and then let's move on to the skewness. So what is skewness? The blue line is the histogram, the density of a Gaussian distribution. As we know, it's symmetric, bell-shaped, nice looking. A left skewed distribution would look like the red one, where I am not going to move the center of the distribution. That's the key. I'm going to move it a little bit down. So, but the right tail and the left tail will be swinging to the left. What does that mean? It means compared to the median level of income change. Suppose that the median worker's income change is 2% per year. Those who normally have a very high income growth, like income growth of 40, 30%, under a skewed distribution, the right tail will be shorter, meaning that when you get promoted, for example, your income doesn't go up by 50%, it goes up by 30%. And when your income falls, it doesn't fall by 20, 30%, it falls by, a lot more. Right skewed will be the mirror image of this. So I'm going to look at a statistic. So you can look at the skewness coefficient, which is what I'm going to show you. This is the third centralized moment of the distribution, as you know. There's another measure that I like better. It's the Kelly skewness, because it is robust to outliers and its interpretation. Like if I tell you the skewness coefficient is -2, we don't have a very good sense about what that means. Okay, how big is that? If it goes from -2 to -3, we don't really, we can say big, but can you write an English sentence with that? Okay, we cannot, but with Kelly skewness we can. So in the paper, we do a lot of things actually using the Kelly skewness or quantile-based measures. So how does the skewness look like at age 25? Notice this is 0, okay? So even at age 25, on average, income shocks are negatively skewed. But moreover, the higher is your income, the more negatively skewed is your income shock. If you are thinking about models, theories of job finding, theories of what we call job ladder, this fits very well with the particular theories that we have. But I'm going to summarize that near the end in the next 10 minutes, in 10 minutes, 15 minutes or so. As you get older, what happens to skewness? It gets more negative. I don't want to depress people in the audience. I'm here somewhere in this figure too. But the older you get, the more negatively skewed income shocks are. What does that mean? Well, think about it, right? The older you get, the higher is your income. The higher is your income. Basically, I'll speak in like US dollar terms. If you have a job that pays $250,000, there are not that many jobs out there that pays $500,000. Okay, so a big upside move in income is not that possible, is not that likely. It can happen, but not very likely. But if you're at $250,000, the bottom is, limitless in a way, because you can lose your job. You can go down to 0. You can get disabled. You can go down to 0. Okay, you can be long-term unemployed. And now when you find a job, that will be the scarring effects we'll see in just a moment. You may not be able to find a job that's anywhere near $250,000. So the older you get and the higher your income is, you are hitting the ceiling at the top, but you are farther and farther. That's what we call the job ladder model. It's like you are climbing a ladder. When you fall, you always fall to the same ground. So the higher up you are, the more negatively skewed shocks are. And the first process I showed you, the standard Volatility model, you don't have any room for this in that specification, because there's no negative skewness there. Whereas in the data, we see very strong evidence of it. The fourth moment now, the kurtosis. 10 years ago, if they told me I would write a paper about kurtosis, I would laugh at them because I didn't know what kurtosis meant. But one day you learn and you realize, actually, it's a pretty important thing. So what is kurtosis? It's one of those things that you know it when you see it. So let me show you the standard deviation of income change in the US data I showed you. It's about 48%, log percent. So let me draw the density of a Gaussian distribution with a 48% standard deviation. It looks like this, we already know. So how close is the data to a log normal? Remember my first question? This is how close, meaning it's not close at all. It doesn't look anything like that. For example, if you look at the mass of workers whose income change is less than 10%, plus minus 10% in a given year. In the US data, 2/3 of workers have income change that are really small. They're like plus minus 10%. Remember, the standard deviation is 48%. Under a Gaussian, the standard deviation is the size of the typical shock. Here, 2/3 don't get anything close to 48%. Whereas under a Gaussian, you have a lot less mass there. You look at the shoulders of the distribution, values around the standard deviation. In the data, there's only 30% of people there. A Gaussian will say there should be 70%. Now, to me, the really interesting one is the tails, which you cannot see here. So I'm going to move from the density. I'm going to take the log of the y-axis so we can see the tails. And this is how the tails look like. Especially if you do statistics or, you know, like some physicists I know are also interested in this. This looks pretty remarkable in terms of the regularity that you see here. Both tails, look at how straight they are. They are exactly linear all the way up to, I don't have it here, but take my word for it here, to +4. So +4 is e to the power 4. It's roughly like a 60, 70-fold increase, and you get a Pareto tail. So the income change distribution in the tails actually is a double Pareto distribution. And this has implications for the length of it. For example, the tail probability, getting a shock of your income going down by 90%. The probability of that is 12 times higher in the data than under a Gaussian distribution. So how does kurtosis vary over with income and life cycle? Well, the higher is your income, the higher is kurtosis. If you are familiar with kurtosis numbers on different time series, like financial data, a kurtosis of 20 is a gigantic number, okay? In statistics, as you know, there are distributions that give you high kurtosis, like, you know, Laplace, for example, they will tap out at 6. And that's considered a very highly leptokurtic distribution. Here you have like 20, you have 25, 30, all the way up to, you know, like this. So the higher is your income. What does that mean? It means a bigger peak in the center. Your income doesn't move in most years. And when it moves by a big amount. Okay. Okay. Higher order risk. Why do we care? I will show you a very simple back of the envelope calculation. We have a current paper. We don't have a draft yet, but where we do this in a much more careful way, meaning we have a fully specified life cycle model with bells and whistles, and the calculations I show you, you know, basically hold there as well. So this is the Arrow-Pratt thought experiment that goes to the 1960s. That's how we derive the risk aversion, relative risk aversion coefficient, right? So the thought experiment is a decision maker is confronted with a gamble. Either tomorrow you are going to consume C times 1 plus delta, and delta is random. So either your utility will be the expected value of this gamble that you consume, or today you can pay me pi, which is a premium, then I'm going to take the gamble away from you. So pi is what we call the risk premium. For a given gamble, what does it depend on? Well, the usual way we do this is we take a first order approximation, Taylor approximation to the left side. We take a second order Taylor approximation to the right side. You rearrange the terms, and then we get an expression that you will see in just a moment. But I will not do that. I will expand on that. I will take a fourth order approximation to the right side. And we often say, well, second order is more important than the third is more important than the fourth. So let's stop at 2, it should be good enough. The densities I showed you tells you no, because the tails are so long, we are nowhere near a Gaussian that will justify a second order distribution. So in the interest of time, I will just rush through the derivation, which is simple. Let me show you how it looks like when you have a CRRA utility function. Okay, this is a very common function that we use. And I'm going to take a risk aversion of 10 to show you some calculations. So the standard Arrow-Pratt formula with the second order approximation is this. The premium will depend on the variance of the gamble, of the bet, and theta, which is the relative risk aversion coefficient here. But when you take the fourth order term, you get the approximation, you get two more terms. And I will let you stare at this. You can tell for yourself that I have risk aversion here, but I have the square of it in the third order term. I have the cube of it in the fourth order term. And if you are curious, you know, the catch is when we say first order is more important than second and so on, the Taylor theorem's residual, okay, can blow up if the function you are approximating has a pole. And this function c to the power 1 minus theta has a pole at 0. So that the residual keeps shrinking doesn't really apply here. And actually, the third order term can be bigger than the second, and the fourth can be bigger than the third. Let me show you an example with real numbers. Okay, I'm going to take a Gaussian gamble. I'm going to evaluate this now without any approximation, actually. I'm going to use, you know, exact solution numerically. And I'm going to say, if I give you a Gaussian gamble with 10% standard deviation. Now, the data, remember, is 48%, not 10%. Why am I assuming 10%? Because I'm going to assume 80% of the shock, income shock, is insured. Why do I do that? Because you will see how big the numbers are even in this case, okay? So this is a lower bound on the importance of higher order moments. If I did with 48%, the numbers would look ridiculously large, you will see. So I'm going to say 80% of the income shock, you save, you borrow, you smooth, because it's a static version of the problem I'm doing. How much premium would you actually, let me move this, would you pay for this? It's very easy. It's like 4.8%, 4.9%. Okay. Now, same thing, 10% standard deviation, but I'm going to use a skewness of -2 and kurtosis of 27. This is taken from the data for a 45-year-old male. So if the data actually has skewness and kurtosis, how much premium would you be willing to pay? About 22%. Okay. So these are not peanuts. These are actually very big numbers. And they come from the fact that for a given variance, if the tails are long, it's much more scary for the individual. If it is left skewed, it is again much more scary. So as you can imagine, we have done this, but there's now a lot of research in economics that finds for taxation, for the value of social insurance policies, for portfolio choice problems, whether you model the income the way we are doing it here, as opposed to the old way, can dramatically change the implications. Even some question about what should be the optimal tax on the top 1% income earners. Okay, there's a paper in the AER 3-4 years ago by Maxim Troshkin, Mike Golosov, and Oleg Sivinsky. If you take a Gaussian income shocks, it's 20%. If you take this income process, these numbers actually that we have here, then you get in excess of 40%. Okay, a top tax rate of 20 versus 40%. Again, that's not a small difference. Now, I have about, do I have 5 minutes? So I will skip these. These are about the mean reversion pattern. There's a cool picture, this one, I call the butterfly pattern. It's in the paper if you are interested. It basically shows that the mean reversion of a shock depends both on the sign of the shock, the ranking of the individual in income distribution, and the size, on 3 things jointly. A worker who is very high income, who receives a big positive shock, that shock will be very transitory. The same worker who receives a negative shock, it will be very persistent. Okay, and that variation, again, we are going to capture in our estimation. So let me show you the process that we estimate. By the standards of this literature we are operating in, this is a pretty scary income process. Okay, it has about like 25 parameters. I prefer parsimony. I'm proud of it because this is the smallest one we were able to find that fits all the facts that I showed you. But the process looks something like this. Okay, so the level of income yi is 1 minus nu, and this nu is a non-employment shock or a scarring effect shock. And this will turn out to be very important, times e to this term here. So remember, before I wrote every income process as a log. The log of income was equal to something. Here I am doing slightly differently. I am writing everything in log, this part, except for a level shock that is the non-employment shock. And I don't have, unfortunately, time to go into this, but this turns out to be the right specification. I'm going to show you just one or two results, but we have estimated more than 250 different specifications over 8 years. And, you know, so we have tried more things than you can imagine. And it turns out that this turned out to be fitting really well. The income, the persistent component is not an AR1 with Gaussian shocks as before. It's a Gaussian mixture. Okay, so the innovation to the persistent component will be a Gaussian mixture. The transitory shock will also be a Gaussian mixture, but the most important one will be this non-employment shock. And it is what we call the scarring effect. Of course, now you might think, well, I keep saying that this hasn't been done before, but every econ model that we know, we have unemployment shocks, right? What's the difference? The difference is huge. That's specification 2 in the paper, if you have the paper in front of you. If you have an unemployment shock to the Gaussian model, it does nothing. Okay, it does nothing. What you need is a shock that is long-term, that's not 3 months of unemployment. It's a long-term unemployment shock, and the recovery of it is very slow and partially permanent. So after you get these big non-employment shocks, even 10 years later, that was the butterfly pattern that I partially skipped. Even 10 years later, in some cases, 20% of that shock you never recover. It's a permanent loss, actually, from those long-term job losses. And this one basically varies by age and by income level to capture the shapes that we have. So we estimated the benchmark process fits very well. We have the figures in the paper. Unfortunately, I don't have time to show you, but pretty much all the figures I showed you so far, you can imagine that we are able to fit them very well. Okay. And the key turns out to be this age and income dependent scarring shocks. Okay, this is my timer saying that I'm out of time, but I'll take 1 minute to conclude. And so what does this look like? What does the income process look like? It fits very well with the way we economists model the job search process over the life cycle and the career path over the life cycle. Okay, when you are young, you change a lot of jobs. Your jobs are unstable, so your income changes a lot. And actually, there's not much kurtosis or negative skewness. Why? Well, because the world looks up. When your income is 10,000, it's very easy to find a job that pays 20,000. There's tons of them out there. Okay, but as you get older, you search for a better job. Your income keeps growing. Okay, and the higher you go, the more stable your job is, because there are not that many jobs that will tempt you away from it. And you have seniority and tenure and so on, which makes it less likely you will lose your job. So there's a structural economic model behind this that can actually generate it. And there are a couple of papers now that are writing these models and showing that you can generate these patterns. So let me, do I have the conclusion slide or no? I think in the interest of time, I'm going to stop here. And if there are any questions, I'm happy to take them.